Hey Shane, how you doing, man?
I'm good. How are you?
Yeah, pretty good, pretty good. Um, yeah, so I was wanted to go over just the section bank stuff. That's what I've been kind of working on the last couple days.
Okay.
But also I wanted to, before we start, I wanted to kind of set this up. I got a couple questions with cars, and then also I'm supposed to take my full length this Saturday, but I don't really know which one we're gonna decide on.
Okay.
So you want to talk about the full length, or you want to talk about cars real quick?
Let's see. Um, Full length. You're up to which blueprint full length?
Let me see.
Five?
No, as I've told you, I've done all the Altius ones before.
Oh,
Uh,
the blueprint ones. I don't know
yeah.
if the full lengths tab in your spreadsheet is for you or for someone else, but it seems like it says up to blueprint full length four.
No, I think I won't pass that. I think I'm like on 8 or 9. 1, 2, 3, 4, 5, 6. Yeah. I have 7, 8, 9, 10.
Oh, so that full lengths tab, yeah, if you get the chance to update it with your scores, you should do that. Um, you
Even the ones I did before.
Yeah, like the ones. So sorry. So um, when was the last full length you took?
Yeah, that was my MCAT. So that was 9/14, September 14th.
Got it. Got it. Okay. Okay. So yeah. So okay, for you, it seems like in your spreadsheet, the calendar for the 23rd, we decided not to take it then, right?
Yeah, because I wanted to see if we can really work on the push on the section bank, which we were supposed to go over today.
Got it. Got it. So yeah. For the 30th, you said that you're up to blueprint full length seven or eight, was it?
I've done all the first 6. I just have not done I've never done 7, 8, or 9 or 10.
Okay. So you could do Blueprint full length seven, and instead of using Blueprint's cars, you'll use either Jack Weston or AMC cars.
Okay.
So yeah, so what that means is, you can start the Blueprint test, like you could do it in sections if you want, but like, you do the CP section, and then when you're done with that, open up like another tab or have the tab already open with passages from AMC or from Jack Weston for it to be like, 53 or questions or 9 passages in 90 minutes. And then you do that, and then you go back to the Blueprint test BB section, psych soc section, and then you'll be done for that.
Okay. But the thing about that
Yep.
is I finished my last couple questions on Jack Weston, funny enough. So I
Okay.
have more questions
So
left. But I was thinking
uh
about doing the Jack Weston full length
so
car
wait,
section.
AMC cars question pack 1, 2 diagnostic tool. You finished all those?
Yeah, I did them before.
Damn, okay, okay. Um
Should we
could
do the Jack Weston full length, the new full length car sections or something?
yeah, now I don't know because I know that they like kind of in those full lengths they use the ones that they've made before. So I don't know if, you know, uh I don't know if it's gonna include passages that you haven't seen before or not.
Okay.
So
Damn.
let me see if I can do this. I'm gonna open up.
And I can also even do like those exam cracker ones or something.
Um, okay. Have you done a pass? So I'm gonna share my screen here. Have you done this passage before?
Number of students in class. Doesn't look could affect how much time the teacher is able to focus. Yeah, it doesn't sound familiar. Doesn't seem familiar.
What about this?
Yeah, this doesn't seem familiar either. I don't think so.
Not for this one either.
Cravings. Yeah, this doesn't seem familiar either. I remember I read a passage something about Igor, but no, this doesn't seem familiar.
Okay. So yeah, that means that you haven't done these. So yeah, you could do the so yeah, blueprint, CP, and then you can switch over to one of the Jack Weston practice exams and just do that cars section timed. And then you'll go back
Okay.
to the blueprint, BB and Psych Soc.
And then what are we gonna do if because there's only four blueprints left. So what would we do after that? Like we
After
just
that,
like
we can kind of figure it out. We can decide if we want to do Altius or not. Um,
yeah, unfortunately I finished all of those. So
uh-huh.
I guess I could go to Kaplan or something.
And for the AIM-C ones, you finished all those as well, right?
Yeah, unfortunately.
Okay. So
At
yeah,
least I just haven't finished the section bank though, so I think that's the only good news about it.
yeah. So yeah, so we'll figure out what to do for the tests after we finish Blueprint.
Okay.
But yeah. Okay.
Okay. Um, yeah, so cars, I've been continuing cars since last Friday.
Hmm.
It's been kind of it's been just highs and lows on cars.
Hmm.
Like the day after I got like a 50%, which was bad. But
Hmm.
like I did like later in the day, so it wasn't as good. But like later the next day I got to back to 70%.
Hmm.
And then yesterday I hit my highest ever. I went 80, I got 82%, so that was really nice.
Nice.
Um, but the thing is like I mean I guess this is just advice, but I feel like a lot of times it took me a little longer than usual. Like overall, the six passages took me like 2 hours, but it took me like, how do I say it? I got stuck on a lot of times on a question. Sometimes I could just get so fixated on a question that like I'm just not allowed to like that I don't let myself like go to the next one. But yeah, I've seen it said as content theme. I don't know if you have advice for that, but I don't know.
Say the last part again.
Yeah, just advice on like what I should do if I get like honestly just get stuck on a question because that's been happening a lot.
So you're saying when you're doing your cars practice?
Yeah, like when I get to the question, there's always a question that I just get so
Got
insanely like stuck on that I just don't move on to the next. And I'm like 6, 7 minutes in. I'm like, dude,
Got it, got it. So, okay, so I guess we haven't talked about timing checkpoints. So, or did we? We haven't, right?
we haven't talked about any of that stuff. No,
Okay,
I don't
okay.
think.
So, so, okay. Timing checkpoints are going to be time or checkpoints where you check your clock. So you're not going to be looking at the clock as you take the test. But once you get to question 20, like write this down. So when you get to question 20, check the clock. You should have an hour left.
Oh, give me 1 second. I
Yep.
also ran out of battery, but I'll write it on my notes.
Okay.
Yeah, I see. You said 20 minutes. No, sorry, 20 question 20. Check the time.
Yeah, the clock, you should have an hour left. So if you have less than an hour left, it gives you a chance to adjust your pace.
Okay.
Then when you get up to question 30, you should have 45 minutes left.
Okay.
And when you get to wait, what did I just say? Sorry.
Question when I get to question 30, I should have 45 minutes left.
Yeah. And then when you get to question 40, you should have 30 minutes left. Okay. So that gives you, so instead of like taking the test and having to look at the clock, which is
Yeah.
distracting, you will only look at the clock when you get up to those questions. So this gives you designated checkpoints for checking the clock and three top like checkpoints where you can change your pace.
Okay.
Now, for that other question, it's no question should take longer than a minute and a half. If it's starting to take longer than a minute and a half, make an educated guess, flag it, and move on. So if we use the checkpoint strategy in conjunction with this, ideally we should uh, finish that last passage or that last question with some time to spare. And that puts you in a good spot because that means that you can then hit review flagged and use your own appraisal. Like, let's say you flag this question, you're 70% sure of your answer. This one, you're 30% sure. This one, you're 50% sure. When you go back to review the flagged questions, you'll start with the one that you're like least certain of.
Okay.
Unless, of course, it's going to take long. Like, if it's a question where, you still have to interpret a graph or you have to do some math, then maybe it's better to do some of the other flagged questions. But the idea here is that when you review your flagged questions, it's after you've already seen that entire section. You've already seen all the passages, you've already seen all the questions, so there's no surprises. Um, as opposed to like, let's just say that I had it so it's like 10 minutes per passage, right? And let's say you get up to, passage 8, you have 20 minutes left, and passage 8 is hard and takes 13 minutes. You're gonna have 7 minutes left for that last passage, right? Because the thing is, passages range in difficulty, and
Yeah.
questions range in difficulty, but all the questions are worth the same amount of points. So you don't want to spend an inordinate amount of time on any one question. So
Okay.
that's the 1.5 minute rule. So yeah, if it's taking that long, just make an educated guess and flag. If it's a calculation problem, your first calculation, if that doesn't get you your answer, flag, move on. Because those types of problems are really easy to get really caught up in.
Okay.
So yes,
Um,
yep.
what should I do about cars then? Because it's like I get so used to writing the maps. Like, I
Uh-huh.
tried a couple without doing the map, and surprisingly, I did all right. And I was kind of in the time frame,
Yep.
but it's still something that I am not used to. So,
Yeah, yeah. So yeah, I mean, like, it'll be what you are doing. But like, have you noticed, like, as you practice, like, you start to see or see the stuff that you would end up putting in the map, but you kind of are doing it automatically as you read through it?
I'm a little confused. Could you say that again? Like, when I'm reading and
Yeah.
I'm already seeing it?
Yeah, so like, so we talked about the strategy involving, like, reading it, identifying arguments, and then, in the map, write down those arguments. Now, in order to write down the arguments, you have to first think about what the arguments are, right?
Yeah.
So, you know, ideally we can get to the point where enough practice of writing out the maps already trains your brain to think about what to write in the maps. And you can get to the point where your brain does that work and you don't necessarily have to write anything. So like for me, when I'm reading like a passage, and I read the paragraph and then I go to write something down in the map, it's like I start writing it like maybe 3 letters down, like in, and then already in my head, it's like, okay, I know what that, argument is in that map, in that paragraph. Kind of like that. And then like second paragraph, I read it, and then when I go to write some stuff down, I've already organized it in my head. So it's just that I don't need to then write it down if I've already organized it. It's kind of hard to explain, but it's like um it's almost like I don't know, like I'm trying to think of a good example, but it's like if you're learning how to add for the first time and you're adding, let's say, like 13 plus 20, it's like you put
Okay.
13 and then underneath it you put the 20 and then you put the line and then you do, 3 plus 0 to get the 3 there and then, the 1 plus the 2 to get like the 5 there. So imagine like that's how you would do math when you're a kid, but with enough practice of doing it that way, you got to the point where you don't need to write all of that out because you've already done the work in your head.
Okay.
So that's the idea here. It's that with enough practice of, because in order for you to write the map, you have to think about what to put in that map, right?
Yeah.
So as you practice, you're practicing both the thinking of what to put in the map and then putting it in the map. So with enough practice, it'll get to the point where you've internalized the ability to think about what to put in the map, and you may not have to write it all out. So
Okay.
so
Yeah, I guess.
basically, yeah.
Yeah. Sorry, sorry, no, you finish, you finish. My bad. Sorry to stop.
Oh yeah, so basically, I would do something like this, like read that first paragraph, make sure you're understanding as you read, right? Um, and maybe spend maybe like 5 to 10 seconds after the paragraph to think about, okay, what would I put in the map, right? AKA what argument am I, getting from this paragraph? And just do that for 5 to 10 seconds after each paragraph. Um, and then at the end of the passage, give yourself maybe like 10, 15 seconds to think about what that main idea is. And that's the most important part. Like getting that main idea down. So,
Mhm.
even if you don't like, let's say, you don't have enough time to like even think about map, like what you would put in the map for certain paragraphs, your primary objective is to come out of the passage with a main idea. And if you have that main idea, that's pretty much the most important thing to have. And then that'll help you with, the questions. So it'll be a process.
Okay.
So yeah.
I see what you're saying. To be honest,
Yep.
I'm, I feel like I'm slowly getting there, but I don't think don't think I'm there, to be honest with you.
Uh,
But
yep.
yeah, I will go ahead and try to do that, I guess.
Yeah. Yeah.
Okay.
Basically,
Nice.
like with the practice tests being timed, like a lot of the issues will auto correct. So
Okay.
yeah,
I see what you're saying.
be in a good position.
Okay. Is there anything else? And for cars, I should just try to go for that 10-minute mark around there for passage. On there, do you think?
Uh yeah, kinda, yeah. Um, so but yeah, just know that not all passages will take exactly that much time. So
Okay.
be so what I mean is if you're on passage 8 and you have 20 minutes left and passage 8 happens to take longer than 10 minutes, it's going to put you in a bad position for passage 9, right?
Yeah.
So, yeah, give or take 10 minutes for a passage, but I'm just saying like it's not going to always be exactly that because there's ranges in difficulty.
Yeah, I see what you're saying. Okay. And then the last thing, yeah, you said something about I remember you saying about a blind rule. Could you quickly go over that again?
Yeah.
It
Yeah, yeah,
says,
yeah. So okay, let's say you take your test and you get 10 questions wrong, like in CP, let's say. What you do is you write down which 10 questions you got wrong. You're gonna try not to look at the answer. I mean, it's fine if you see it, but you're just gonna write down the ones you got wrong, right? And then you're gonna do a second attempt at the test, untimed, only doing the questions you got wrong the first time around. So the purpose of this is the fact that um, questions that you get wrong on the test could be because you don't understand it, but it could also be because you're on a time crunch. You don't have time to actually give it a shot. So
Mhm.
just go straight to review, which is reading the solutions. For the questions that you never got a chance to answer, it's almost like you're wasting that question, right? Because you never
Mhm.
got a chance to actually try it out. So that's what the blind review does. It lets you redo the questions you got wrong the first time around without the time constraint. So we can separate the ones that, this is something you got wrong because you didn't really know this concept or idea or whatever. And this is a question you got wrong that you otherwise know how to do, but you're on a time crunch. You're running out of time. So you didn't get a chance to. So that's the blind review. So that means you're going to do that blind review. So let's say out of the 10 questions, 5 of them make sense, 5 still don't. Then you'll do a regular review, which is like normal. You read the solution. Um, And then after the regular review, whatever questions still don't make sense, we can go over. So that way we don't have to go over like all of the ones you got wrong. We'll just go over like the really high priority ones that you still don't make sense even after you've tried it untimed and after you've read the solution and all of that stuff. So that can make our sessions efficient. But it doesn't always have to be like that. I mean, you could even get a question right, but if you're curious about how I would approach it, um, that can also be something that we do.
Okay. Okay. Sounds good.
Yep.
All right. Yeah, so what I wanted to do was I don't feel like we've practiced like mapping out like CP section stuff.
Yep. Yep.
I just do a
And
passage. I
BD.
just what's up?
Oh, and so I would say for the stuff that I'll show you about how to write out stuff for yeah, for the science passages is going to be more relevant to the BB section, but well, actually, okay, so we can do this one. So
Okay.
so this is what we're so it's going to be a little different. So what we're going to do is so yeah, I'm going to have you read out loud, but there's going to be so I call them buzzwords. They're
Hmm.
words that you so okay, so the reality is all of these passages are from like published papers from like PhDs and doctorates and stuff, right?
Yeah.
So we're not expected to understand everything here, right?
Yeah.
What we are expected to know are like the basic science concepts. So buzzwords are words that are those basic science concepts that we are expected to know that they'll likely ask us questions on.
Okay.
So, and I'll show you what I mean as we do this passage.
Sounds
So,
good.
so yeah, you can read out loud slowly, and if you want, you can also tell me like what you're thinking of at that moment, but I'll interject and kind of ask you uh
Good.
certain things. Yep.
Uh, lysozyme is an enzyme that kills gram-positive bacteria by cleaving N-acetylglucosamine oligosaccharides.
All right. What is gram-positive bacteria?
Yeah, so gram-positive bacteria is a type of bacteria that is differentiated due to its it has a very big polysaccharide uh a peptidoglycan layer. There we go. That's the word I was looking for. Peptidoglycan layer.
Well, what you so layer, but what do you mean by layer? Like
It has a very thick peptidoglycan layer compared to a
when you say
gram
layer, though, what do you mean by layer?
wall. Sorry, wall.
Good,
Wall.
good.
Wall.
Because a layer could be a membrane, it could be a wall, right?
Yeah.
And there's a great difference between the two. A membrane is flexible, right? A wall isn't flexible, right?
Mm. Okay.
So a lot of times, so a lot of like the way that most antibiotics work is they put holes in the cell membrane. Sorry,
Mm.
in the cell wall,
Mm.
which can cause a lot of things like and also like if you have a sore throat and you gargle with salt water,
Yeah.
you're producing a hypertonic environment, which causes the water from inside of the prokaryotes, the bacteria, to be leaving the
Mm. Mm.
you know the,
That's
the
interesting. I didn't think about that. Okay, that's cool. That makes sense.
yep, and also the peptidoglycan cell wall is the thing that picks up the stain.
Yes.
That's why for a gram positive,
It's purple, right? I
it's
think, in
purple because it has a
purple.
thick wall, right?
Mm.
Now, the gram negative has a thin wall, so it won't pick up as much of the stain, so it'll appear pink.
Mm. Yep.
Now, is that the only difference between gram positive and gram negative? The how thick their cell wall is?
No, I think there's like this thing, what is it, LPS, lipopolysaccharide on the gram negatives.
Sure, sure. Anything else like more? So I'll just tell you. So the gram negative also has an outer membrane.
Mm. Okay.
So gram positive has a membrane and the cell wall. Gram negative has the inner cell membrane, the thin cell wall, and then the outer cell membrane.
Okay,
Okay,
sounds good.
good. Now, oligosaccharide, what's that?
That's just chains of sugars.
Good. All right. Oh, and what does lysozyme do?
Lyso, lysozyme breaks down lipids, right? I think lipids. That's a lipase. No, never mind.
So, what does the passage say?
It's an enzyme.
That
What's up?
enzyme that
Oh yeah, by cleaving. Oh yeah, cleaving the knapsack. Yeah, cleaving the knapsack. So it just
leaving the what?
says yeah by cleave. It's an enzyme that kills bacteria by cleaving the N-acetylglucosamine oligosaccharides. So I guess it cuts down these sugars.
Good. Good. Okay.
One product, NAG3, has a high affinity for hen egg white HEW lysozyme. Affinity constant has a high affinity for lysozyme. High affinity constant is 1.3 times 10 to the fifth molar to the -1. Its delta H is -50 kilojoules per mole. Its delta G is -30 kilojoules per mole. Um, Structural studies indicate that NAG3 makes hydrogen bonds with a D aspartic acid 59, tryptophan 62, tryptophan 63, aspartic acid 101, asparagine 103, and alanine 107.
Anything seem off?
Yeah, I don't know how you make hydrogen bonds with a tryptophan.
Mm,
I guess you can, but
what do you need to make hydrogen bonds?
yeah, you need a hydrogen bond. Yeah, I guess you need a donor and an acceptor.
I mean, like
Acceptor is
what particular elements?
OH.
Sorry. So I mean, fawn.
Yeah, fluorine, oxygen, nitrogen.
So you need those for hydrogen bonds.
Hmm.
Okay. Now, what do you remember about tryptophan?
Tryptophan has that two ring structure, like the five ring, and then it has the
All right.
other bigger ring on it.
Tell me about those rings. What are they composed of?
They are aromatic
Sure. What are they composed of? Like, what are they?
carbons, just
Just carbon?
carbohydrate, carbons and hydrogens.
Just those?
Well, the side chain, yes, but then you do have the carboxyl group, and then you have the amino group, and then
Any other amino acids seem a little weird here? It's okay. We can continue.
an alanine, I guess.
What's that look like?
Valine, alanine, glycine, alanine. It just has a same thing, carboxyl and an amino group, hydrogen, and then it just has a methyl group.
Okay. So, okay. So we have alanine and we have tryptophan. And you remember what alanine looks like. You don't remember what tryptophan really looks like. So which one would be more weird?
I guess tryptophan, because I don't remember what it looks like much.
Here's an analogy. Let's say someone asks me x squared is equal to 4. Um, and I have to figure out actually, okay, let's just continue.
Okay. In a cleft in HEW lysozyme that is adjacent. Okay, well, HEW, okay, that was lysozyme. I think the next three was, sorry, that's a high affinity for. A cleft in HEW lysozyme that is adjacent to the catalytically active D52 and E35 residues.
Okay.
Unlike NAG3, okay, NAG monomer interacts weakly. So yeah, NAG monomer interacts weakly with HEW lysozyme, and it is not possible to measure KNAG or delta H of its interaction directly. Okay, so they're introducing another new thing, an NAG monomer, which seems different from NAG3.
How's it different?
Apparently, it interacts weakly with HEW lysozyme because the other one, NAG3, has a very high affinity for
Yeah,
it.
but what like that could be some effects of it, but what separates NAG3 from NAG itself?
Oh, seems like the X. I think maybe it could be the sugars.
So NAG3,
Has three sugars, I guess.
yep. So
Okay.
that's why when they say NAG without the three, they say monomer.
Oh, okay. I see it now. Makes sense. Researchers used competition isothermal titration calorimetry to measure the heat of interaction of NAG with HEW lysozyme. So they assume sort of variation of calorimetry
Okay.
to see how they, yeah, to just see the heat of interaction. HEW lysozyme, 1 milliliter and 0.1 millimolar was titrated with 25 injections of NAC3, 10 microliters, 2.5 millimolars, in the presence of various amounts of NAG, and the heat associated with each injection was measured. Modeling of the heat per injection curves gives a parent association constant K. A
Okay.
lot of information. Um,
hmm So, okay. So what's this issue? Like, why do all this titration stuff about NAG? Why can't we just, I mean, we have information for NAG3. Why can't we just, you know, have information for NAG monomer?
yeah, it seems that the difference in sugars tends to affect how it's able to interact. So it makes it harder to see the variations in delta H. So it seems like they're using this technique to be able to identify um, the heat of interaction as they say it is. So I'm guessing that's why.
All right, good, good, good. Because yeah, NAG monomer interacts weakly with the Hue lysozyme, and therefore it's not possible to measure KNAG or delta H directly, right?
Yeah.
Okay. Now, what? Tell me what happens in a titration.
So now I was thinking about acid-base titrations. So
Sure, that's fine.
as you essentially you start off with a certain solution, I guess, of like an acid. And as you add more and more base, like as you add more and more base, it gets to the point where enough of base that you add, it completely neutralizes the acid.
Is there a name for that?
Yeah, so that's the You got the half equivalence point, and then you got the equivalence point, I guess, when it's completely titrated or completely neutralized.
So what you described, is it the half or the equivalence point?
When they're completely neutralized, yeah, I think that's the equivalence point.
All right. What else about the equivalence point? Like, you know, what else about it? Like what can you tell me about it?
So if you're neutralizing it, so at that point you will completely have zero acid, I guess, and completely have the base form of it, or the conjugate base, I guess, the neutralized form, the negative charge, I guess.
Okay. This is kind of what an acid-base titration would look like, right?
Yeah.
All right. So where would the equivalence point be?
Uh, Somewhere like here, right? It would be here.
Okay. So you said, what about the amounts of the acid and the base?
Yeah, so the half equivalence point, you have like
Oh, I mean,
um
for equivalence
you
point.
just equivalence point. Oh yeah, you have completely all of you have like basically no acid left, I think, at that point. Like everything is just base.
So let's say that we start with a pH of 1 and we end up with a pH of 14 and equivalence point is at 7.
Okay.
You're saying the equivalence point is when it's all base. So wouldn't that be this region?
Oh, that's right. So I guess the 7 would be the half equivalence point. So, and then the fourth, this region would be the equivalence point then, I guess, right? If
So
they're all base,
this is
yeah, you're right.
so this is still the equivalence point. Don't worry about half equivalence point because that's for a weak acid base titration, aka like in a buffer.
Okay.
But so okay, so this part is when you have more acid than base. This part is when you have more base than acid. So what might this be?
Yeah, when your acid is equal to the amounts of base.
Good. Hence equivalence point, right?
Hmm.
Equivalent amounts. Now,
Right.
you say when I say equivalent amounts, what does that mean exactly?
When your deprotonated and protonated state is 50-50.
Um,
Or
so
pH.
what
Yeah, your overall concentration is 1, I guess. Like when you compare it to both of them.
so
Yeah, I'm thinking of numbers. Okay, yeah.
so okay, so let's think about it, right? Um, I'll give you choices. Volume, molarity, like is it when they have the same volume?
Um, when the volume of, I guess, because in this case, I know it's always typically the volume that you add of whatever base is equal to the moles of acid or whatever that you start off from the beginning.
All right, okay, okay. So the equivalence point, they would have equivalent amounts of
Moles.
moles. Good, 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 good. Because like let's say we had HCl plus let's say strong acid, right? Titrated with strong base, NaOH. Each molecule of hydrochloric acid is neutralized by each molecule of sodium hydroxide, right?
Mm-hmm.
And mole is just another way of saying molecules. It's just Avogadro's number of molecules, right?
Mm-hmm.
So good, good. Because I always ask this question to students and they can tell me like that they're equal amounts, but they're gonna tell me something like, let's say, equal amount of volume. Why wouldn't that work?
Equal amounts of Y equivalents of I think it's because I could be wrong, but
So if
typically you're always working with very small like concentrations of acids. So taking
so
in big volumes would be a little too much,
so
I think.
like all right, so for instance here, Q lysozyme was titrated with NAG3, right?
Yeah.
Now, if we had the same amount, let's say 1 ml of this and 1 ml of this, would that be equivalent?
Mm,
Because
yeah,
look,
I guess. Well, I mean, hmm.
because look at this.
It depends. I would have to change that to moles to know that's equivalent, right?
Exactly, right? Because volume doesn't tell you anything about the number of moles because volume, if you have equal volumes and they have different molarities, it's not going to be the same number of moles, right?
Yeah.
Same thing with molarity, because another thing students tell me is like they have the same molarity. So you could have the same molarity, but you can change molarity by changing the volume, right?
Yeah.
So
It's-
so an analogy I use is like mass versus weight. Your
mm,
weight on Earth is different from your weight on the moon,
mm,
right? Because it depends on the gravitational field, right?
yeah.
But your mass is the same no matter what, right?
Mm,
So molarity, which is moles over liters, you can make the molarity go up by reducing the volume. Like, aka you can artificially change the molarity by changing the volume without changing the number of moles, right? Right?
makes sense. Yep.
Yep. So equivalence point equal moles of so the thing in like the beaker is the analyte, and the thing that you dropwise add is the titrant. Okay, good. Good, good, good. Okay.
So wait, so just to kind of put this together, um, so at the equivalence point, it's typically just the moles of so it would be okay to say that it's the volume needed to get the moles of solute equal moles of acid equal to the moles of base, I guess.
Yeah, so you can generalize it by using the word analyte and titrant. So the equivalence point is when the moles of the analyte equal the moles of the titrant.
Okay. And it's again what you said, right? We can't use volume because it's like we can kind of change the volume around, which could affect the molarity, overall molarity and stuff.
Mm-hmm.
Okay.
Good.
Okay,
Continue.
so modeling the heat per injection curves gives you apparent association constant K app. Okay, K app is mathematically related to the affinity constant of nag. Okay, K nag by equation one.
All right.
Yeah, yeah, sorry, I was just gonna get lost what K app was, but yeah, the apparent association constant. By plotting K nag 3 over K app versus nag concentration or molarity, the value of K nag can be determined.
Okay. Now you see this plot, um, and the
Yeah.
equation. Anything no you notice anything? Like I know that's a vague question. Um,
Yeah.
but yeah, do you notice?
Just you're saying about this equation itself?
Yep. And the figure, because that
It's a bit odd. about the I don't know where they got the one plus part. I don't know if you're talking about the one plus part or the I guess the one plus KNAG part.
So what does figure two look like?
It's just like a linear plot, I guess.
All right. What and what's the y? The y-axis?
KNAG over KAP,
What's the x?
NAG concentration.
Okay. Now think about that.
Oh, Y equals MX plus B, I
Yep.
guess.
Yep.
The B is supposed to be one. It kind of sounds cont there.
Yeah, the y-intercept, right?
Yeah.
And
Yeah, okay.
go on, keep going.
What's up?
Oh, keep going. What's the other stuff?
Oh, yeah. So MX, so the M is KNAG, which is, I guess, the slope.
Good.
And then Y, well, yeah, Y, this is Y.
Yep.
This is one. And then MX. And then X is, yeah, the X is the nag, I guess. And then M is
Good.
the slope, I guess.
Good. So,
Okay.
yeah. So far, so we talked about those buzzwords, and there's other things that I kind of was like, notice anything, blah blah blah. That I, we'll you'll see what I mean by that. Um, but yeah. So when you see like, so you want to be able to read very actively and think as you're reading. So you want to constantly look for, in addition to those buzzwords, like patterns or things that you notice. So, so when I see this, like what I was thinking of was, the slope intercept form. And we see the plot of that as well here. So
Mm,
anyway, um,
right.
any questions so far?
No, no,
All right,
no.
go for it.
Questions?
Yep.
Okay. Yeah, so it says, according to the passage, what type of bond? Let me put your. Okay. Yeah, according to the passage, what type of bond is cleaved by lysozyme? Back to the first sentence, it says that it cleaves these sugars. Um, Probably not a peptide. I don't know about a phosphate ester. I'm kind of wary on that too. And pyrophosphate, that seems like another phosphate, so I'm not sure. But yeah, I mean, we know that I guess putting sugars together, we can kind of, that's a glycoside formation. So I think C would be a good answer.
Good. And what did you say about the pyrophosphate?
Yeah, I don't really know what that is, but I mean, it seems something related to phosphate. So I was like,
Do you
I
know what
think,
uh do you know how to draw a phosphate molecule?
mm, just gonna try to put from memory. Can I annotate here?
Yep.
Okay. So like this, and I think it has an O here. O, something like this.
Open up your periodic table.
Yeah. Give me a
Oh yeah,
second
you
here.
have to. Yeah.
Yeah.
Okay. Phosphorus is here. How many valence electrons does it have?
One, two, three, four, five.
Okay.
So I guess we gotta take out a couple bonds.
Do you remember,
Um,
remember what charge phosphate had?
Charged phosphate had
Or maybe think of phosphoric acid.
PO4 3 minus.
Mm. Okay.
Okay, so that's PO4. Write that down here. Oops. Um, so I guess it would be just one double bond, I guess.
Good.
Oh, too short.
Good.
Okay.
Okay, so you're expected to know what this looks like and even more like how this interacts with stuff. So good. And then when you drew it for the first time to check, you saw what we did, right? We went to the periodic table to see the number of valence electrons, right?
5.
Yeah. So that's how you can tell if the structure you drew is what it looks like, right?
Right, because it's like 1 here,
Yep.
and then 3, 4, and then 5.
Yep.
Right?
Yep.
Okay.
Good. Good. So now, so pyrophosphate. So this is an inorganic phosphate because it's phosphate on its own, not bound to an organic molecule. Whereas like ATP would be phosphates bound to the organic molecule of the ribose sugar and the adenine, right?
Hmm.
So a pyrophosphate can also be written as PP lower subscript I, and it's just two phosphates bound together. So basically this.
Pyrophosphate. Okay. I'll write that down real quick.
Yep. And yeah, and then for these types of bonds, you also want to know what their organic chem names are. So like what is this bond? Or yeah, what's this bond?
No, it's in DNA, so that's phosphodiester bond.
Yeah, good, good, good. And then a peptide bond is what like functional group.
Amide.
Good, 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 good. Um,
What's a phosphate? Phosphate ester? That's
oh, that's just phosphate ester, like not a phosphodiester, but phospho like one ester.
so that would look like. Let me see. So like just for the carbox like a O group, like 2, there's a OR. Like this would be a phosphoester.
Mhm.
Or no, never mind.
Yeah, just remember,
Got a
it'll
double bond.
be basically that.
Oh, it have OR everywhere. Oh, okay.
Hmm.
Interesting. Okay. Oh, oops. Did not. Sorry.
That's fine. Um, okay, good. All right, yep. Let's go to the next one.
What is the approximate value of delta S? I'm guessing that's asking for entropy for binding of NAG3 to HEW at 27 degrees Celsius. So I guess it's asking for thermodynamics here, so feel like it's a feel like it's a delta G equals delta H minus temperature times
Mhm.
delta S
Yep.
equation. They're in Kelvin, so we gotta convert this into Kelvin. So I think that's like 300 Kelvin.
Hmm.
Um, and it's in joules. So I guess we could. So we have negative 30,000. I'm kind of just doing this in my head. Negative 30,000 plus 50,000. So we have 20,000 joules left divided by 300 Kelvin. So that's, I would say about 60. Yeah, 66. I'm like thinking about 60. So I feel like this kind of goes around the range. So I think that's C, but I don't know.
So
I might have missed the
very,
math. But
very impressive, but uh, something is happening here. Like, write it out. Maybe you'll see it that way.
see if this works. There we go. All right. Okay. Delta G. The heck? Huh. Um, so yeah, right. I get negative. It's gonna take me a little long to write the units, but
Here,
um,
so check this out. So I'm gonna first rearrange this algebraically.
Oh, okay. Sure.
So we have our, so you said our negative, um
30 kilojoules.
minus negative,
Uh, -50.
right?
Yeah.
So you're gonna get something slightly different here. Sorry, what I mean is, whoops.
I did it on my iPad here. Let me see. Got 20 kilojoules over per mole over 300 Kelvin.
Okay.
So 20,000. I guess we can do 20,000 joules over 300 Kelvin or per mole, I guess. Uh, yeah, I guess a mole. I guess you're talking about the mole, really?
Oh, I just mean the
I'm not
sign,
really sure what you mean.
the the signs.
What was it, negative temperature? I guess technically, because it's if we do subtract the delta H, it would be we would still be left with negative temperature times delta S. So we're supposed to divide it by negative T. Is that what you're talking about?
Because of the subtraction, right?
Yeah. Okay. So it would be -67, I guess.
Yep.
Okay. Sounds
So
good.
very impressive, right? But I always say just slow and steady. Oh, no, slow and systematic so as to
Okay.
avoid errors like that. But still very impressive.
No, I think I'll definitely start writing that out. Probably should start writing it. Okay.
But no,
Thank you.
yeah, very, very impressive.
Um, Based on these structural studies, when NAG3, when NAG3 interacts with amino acids in HEW, it can hydrogen bond to the side chains of the amino acids at all of the positions except for the amino acid of which position. So let me highlight that real quick. So we have 62, 101, 103, 107. Ooh, interesting. Um, okay. So I definitely feel like I can take out 101 and 103 because it's asparagine and
Sure.
they have the,
Yep.
the charge they could hydrogen bond,
Okay.
FON. Um, so really between tryptophan and alanine. Uh,
So this is what we were
I'm
kind of talking
thinking,
about before, right?
yeah, I'm thinking if
So
tryptophan has the nitrogen in the little
so
five-minute ring for some reason.
so let's do this, right? So continue. So I was like, this is what I was talking about when we were talking about this. Okay, so alanine, has a side chain of what?
CH3.
Now, can that hydrogen bond?
No.
So if you're left with something can't hydrogen bond, and then something whose structure you don't know,
Hmm.
that one structure that you don't know must be able to hydrogen bond, right?
Yeah.
Because you know that this one can't,
Yeah.
right? So that's so that remember when we were talking about it when we first saw it, and I was
Yeah.
asking, okay, tryptophan, you don't remember the structure exactly, but alanine you do.
Hmm.
And I was asking which one would you pick, and I think you said tryptophan because you don't know it. But now do you see that if you're left with something that you know is not gonna be able to, like in this case, we know the alanine cannot hydrogen bond, and we are unsure whether tryptophan can or cannot. But if it's a choice between the two,
Mm.
Alanine, we know can't hydrogen bond. So the tryptophan, no matter what, must be able to hydrogen bond. Okay.
Tryptophan. Okay.
Yeah. And now
That-
I'll tell you what it looks like. It's going to be the two rings, but when I was asking, like, what are they composed of? So they're heterocyclic rings, which means that they include things that are not just carbon. So they include nitrogens.
Okay, oh, so you have nitrogens. Okay.
So, like, like, I always say, like, I want to give you multiple ways to get the, because I could have just been like, well, this is what tryptophan looks like, and it's a nitrogen, so yeah, it can hydrogen hydrogen
Yeah,
bond.
yeah, yeah.
But I wanted you, so that's why I first was like, okay, anything seem off, and we kind of went like that, and and I tried not to like, give you the answer, but
Right.
give you logical ways to figure stuff out. So, because another thing is like I hate it when people say like, okay, you need to just memorize all the amino acids and like what they look like, um,
Yeah.
and that this is polar, this is non-polar, etc. But like that's not as useful as being able to see like, okay, like these are the amino acids that like you want to be able to look at a molecule, and so like this over here you don't need to be told if it's polar or non-polar, right? You should be able to tell based on like, an electronegative atom being bound to something will pull electrons towards itself, creating a polarity. So, so yeah. So basically,
Okay.
so yeah, when you read that, and lots of passages you'll see are going to be about an enzyme and amino acids at the enzyme's active site. And those amino acids will have something special about them. They'll be able to either be charged or hydrogen bond or something like that. So what they do a lot of times is to figure out which ones matter, they make like a variant. So like it'll be like D59A or
Mhm.
W52A. And the variant is always going to be like alanine because alanine doesn't do anything special. So if they change the variant for, the D59 and the kinetics of the enzyme gets completely messed up, we know that the D59 is an important position.
Mm.
You'll see a lot of questions about that. Um, but yeah,
Yeah. I see what you're saying. Okay.
good. So okay, but if it says that it makes hydrogen bonds with these,
Hmm.
how does it then make hydrogen bonds with alanine? Because it does say that it makes it with alanine.
Oh, that is true. Uh, hmm. I mean, I'm thinking that it
Yeah, tell me.
has to do something with that carboxyl or the amino group. That's the only other possibility. I don't see any other
Yeah, yeah.
possibility.
The backbone, right?
Yeah, okay.
Because every amino acid will still have, well, amino acid, right? Amine group,
Mm.
carboxylic acid group. Those groups can participate in hydrogen bonding, right?
Yeah,
And this question says side chains, right?
yeah,
So, so yeah, so it's like, this says that it can make hydrogen bonds with alanine, and we know that it can't make it with the side chain of alanine, but if it says that it still makes it, it must be the backbone.
okay.
Yep.
Okay. Sounds good.
Hmm.
What quantity of NAG3 was required to reach the equivalence point in the titration? Okay. Let's see. There's a heat of interaction. So the left one was HEW alone, and then H in the presence of NAG. So probably just looking at this one here. And we talked about the half equivalence point.
Well, We mostly talked about not that.
Oh, yeah, that's a good point. Yeah,
Because
yeah, this is
the
an acid base. Yeah, this isn't an acid base or anything like that.
no, like that stuff is still relevant, but half equivalence point is going to be when you have like like a buffer. So
Hmm. Wait, did I say half equivalence again?
oh yeah, yeah.
Okay, okay.
So yeah, so like something like that where it's like a weak acid being titrated by like a base or something, like you'll have a very long horizontal region where the pH doesn't change because it's acting as a buffer. And so
Hmm.
here, like the midpoint of the mostly horizontal aspect of it is going to be your half equivalence point. Okay.
Hmm.
But that's only for when you have like a weak acid base titration, aka a buffer situation. But when you have a regular situation, it's just the typical sigmoidal curve, S-shaped curve, right? And there
Hmm.
for that, there's no half equivalence point because there's no need for it. But there is the equivalence point. Okay.
Okay.
Now, what does the equivalence point mean?
Yeah, so when we said that it was the essentially the moles of whatever you're starting off with, and then the moles of whatever you're adding are equal to each other.
So what you are starting off with is the analyte, and
Analyte, right?
the
Okay.
titrant is the other thing. Good. So,
Titrant, analyte, titrant. Hmm.
okay.
So in this case, if it was saying what quantity of NAC3 was required to reach the equivalence of point of the, so in this case, that as you said, the analyte or titrant we're adding, analyte, I guess, is the lysozyme
Okay.
titrated with it, the titr, and this is the thing that they're adding it to, the analyte to the titrand, I guess.
Wait, say that again?
This is the analyte, and you said this is the analyte, the lysozyme that they're adding, and then this would be the tit
Yep.
titrand, right? This would it does not be referred to the titrand?
No, no, no. You're right.
Okay, okay. So the molar ratio.
Do we even need that?
Hmm. I guess wouldn't we need the concentrations though of these two things?
So what's being given there?
Well, NAC3, we got the concentration of the lysozyme, and then we have 25 injections of NAC3 with 10 microliters of 2.5 or 10 microliters or 2.5 millimolar
So we have concentration and
solution on volume.
okay. What can we do with those?
We can change that into moles
Okay.
of whatever that we got.
Okay.
Okay. So I guess they're asking for quantity of NAG3, so maybe we can start off with NAG3, I guess here, 10 micro, continue this into moles.
So they said 25 injections of NAG3, right?
Yeah.
So this would be for each injection, right?
So you just have to multiply whatever you get by 25
So
times 20.
in this curve here, where would it be after 25?
Around here, right? The equivalence point, right? No? Or I guess, wait, it's pretty short-lived. 25 injections.
So like the entire sigmoidal curve is what you get after you do the 25 injections. So
Okay.
So 25 total injections gives you the S-shaped curve. So that means that 29 after, sorry, 25 injections, it should be like up here,
Hmm.
right? So how do we know how many injections will be giving us the equivalence point? Because 25 will be up here. Like if it's like one or two injections, it'll probably be down there. But
Mhm.
for that, that's a little difficult, right?
True.
So check this out. What, so the titrant we add drop by drop, meaning we add moles, mole by mole.
Okay.
But the analyte never changes. The moles of the analyte never changes, right?
Yeah, you always have the same concentration, it seems.
When you say that, you mean same number of moles.
Sorry, yeah, most.
So for any titration, like a shortcut to figure out the equivalence point, uh, would be simply to find the moles of the analyte, because that doesn't change. The titrant will change and
Mm.
it'll add dropwise until it gets to the equivalence point where they're equal, but then it'll overshoot to give you the full S. But the analyte number of moles of analyte doesn't change. So the equivalence point would be when the moles of the analyte equals the moles of the titrant. And since the moles of the analyte don't change, you can just solve for the moles of the analyte, and that'll be how many moles of the titrant you need for the equivalence point.
Okay, yeah, no, that makes complete sense.
Yep, yep.
Okay.
Hmm.
I guess we can quickly do this, I guess. Let's see.
Yeah, you could probably do some crazy fast math in your head over here.
No, probably not this.
Well, we can get rid of two choices though, right?
Uh, Actually, yeah, you probably, I mean, I think they have both millis, so, well, I don't know about ends, so, actually, wait, I mean, we can do that way then. I didn't
No,
think about it then.
I mean the
I guess we can
25.
get rid of, oh, sorry.
Sorry, what were you saying?
Oh, no, I can hold it. No, you're fine. What were you gonna say?
You go. Tell me what
Okay. I was just thinking, you said what answer choices we can get rid out, and
yeah.
I mean, we know molarity is M equals moles over liters. So if
Oh,
both of them are M, so it'd probably be -6. So we can actually, I feel like we can take out these, but I don't know.
no, oh, so this is what I was gonna say. So if we did math with this, it's gonna have some like one in it.
Hmm.
The 25 can only come from this,
No.
right?
Yeah, okay. Makes sense.
So we can get rid of the ones with 25, right?
Okay.
Okay.
Okay. Um, so yes, we got what, 0.1 millimolar.
Yeah. Now, I'll also say that it would be good to get into the habit of already putting these. So what I mean is the zero point 0.1 millimole, I would write as zero point 0.1 E -3 molar.
Okay.
And the 1 milliliter, 1 E -3 liters. So
Okay.
you can, if you do that, then you get to skip the step of, you know, converting
Yeah.
it because you can do that.
Just do it automatically.
Yep.
Okay. Well, I guess we're just gonna multiply it anyways. So I guess we can just do one E liters and then 1 times 0.1 times uh yeah, 0.1 times 1 is 0.1, I guess. E what why do I keep doing that? negative, we add them, so it'd be -6. Hmm. Okay, so yeah. Okay. So yeah, it would probably be, so it's 0.1. It definitely wouldn't be D. So it would probably be B, because if we do right to subtract, it should become -9, and then you'd have 100 nanomolars.
Exactly. And also, if this is E -6, that means it's zero point 0.1 micromolar, right?
Yes.
And this is the only thing with micromolar, and it says 100, and that's not
Mm.
that, right?
Yep, agreed.
Yep. There
Okay. Okay. And so again, to like just to reiterate what you said,
Yep.
um, so again, the equivalence point, right? So we went over, it's like it's essential, like this is essentially where all of it takes to completely neutralize it, but it still wouldn't be, it would go over it. And a good way to essentially find the equivalence point, as you're saying, is like the concentration of the titrant here in this case.
Analyte?
Analyte, keep confusing that.
Yep.
It's always going to be the same. It's not going to
Yeah,
really
yeah. So
change.
like this region over here is when you have more analyte than titrant. This region is when you have more titrant than analyte. And yes, this region or point, equivalence point, is when they are equal.
Okay. I'll take
So
it.
when they said here, titrated with 25 injections, that's for the entire S-shaped curve. So that means the 25 is going to be up here. So it has to be less than 25, but we can't, really do it that way. So yeah, the trick would be just to do the thing for the analyte.
Okay. Sounds good.
Yep.
Mm. What was the experimentally determined value? Oh, I'm gonna use the bathroom real quick if that's okay.
Yep.
What was the experimentally determined value? KNAG from the study. Shane?
My bad. I went to the bathroom too.
Oh, okay, okay.
Yeah.
All right, sounds good. Yeah, so what was the experimentally determined value of KNAG from the study described in the passage? Okay. Yeah, I think the only value we have is probably around here. So we can kind of use this equation here, essentially, I feel. I mean, I think at this point, I feel like we can just kind of chug some points in at this point. Um, into this equation.
Well, remember what we said about it?
So it was in the y equals mx plus b.
Yep. So the KNAG is
Yep,
what?
slope.
All right.
Okay, so essentially just having to find the slope.
Yep.
I mean, you can correct me if I'm wrong, but like I think the only method is there another method besides like rearranging this to find for KNAG, or is there anything a little simpler? Because that's the only thing I can think of.
I don't know. Just find the slope, right? Remember in like eighth grade math or whatever?
Right, like rise over run, I guess.
Oh, yeah.
Okay. So you can use I guess I can use this point. So like 2 to 0.020. So that is let's see, brain cannot do that for some reason. Um 2 over 0.021 2. Getting 100, but that is not.
Wait, so when you said okay, so it's change in y over change in x,
Hmm.
right? So if
Oh, your Y is, yeah, your Y is it. Okay.
so first we have a point at 0
Point 0.6 kind of sounds like.
and
Oh
then
no, oh my God, it's not even at 0.0. Oh, okay.
it's at 1, right?
Oh, so 1, right? Okay, okay, 1.
That's
Okay.
what because here, remember this is a y-intercept.
Oh, that's right. Oh my God, you're right, you're right, you're right.
Yep. And then we can
So
just use yeah, this point. So that'll be 0.02 comma 2.
okay. Yeah, so it'd just be 1 over this. So yeah, that would be what, 50, right?
Yep.
100 divided by 250. Okay.
There we go.
Yeah, that would have honestly, I probably would have sat down trying to simplify
Yeah, yeah. So yeah,
all
that's why
this.
you want to constantly be like it was funny. I was going over a problem with a student and she was like kind of saying like, "Oh yeah, I didn't expect, to have to do math here." And I'm just like, always expect everything. So like, because like, because people can read this and be like, this is BB or CP, fine. But they'll be like, okay, this is bio stuff, blah, blah, blah. Or, they're not going to be thinking slope intercept form when they see something like this, but that's what I want you to start think like I want you to be thinking actively.
Okay. Typically, I mean, um I think I might have made a mistake a lot of times on CP, or I kind of got the habit was just not really not really reading the passage and just kind of going through the questions because it seems like a lot of times the content seemed off, but I mean I see a
Yeah.
lot of times today it's like a lot more
Yeah,
helpful
yeah.
than I thought.
So,
Yeah.
so two things about that. So, I would say that if you're running out of time and it's CP, that's a last resort you can go to. But for cars, BB, Psych Soc, you want to read that passage first. Okay? So only for CP and only last resort, running out of time. Now, aside from that, the thing that we're doing uh is that when we're reading the passage, we're reading actively, we're anticipating questions that they'll ask us by recognizing those buzzwords.
Hmm.
So you saw like every step of the way, it wasn't like because what you don't want to do is that a lot of people do is like they kind of read something fast and then after they're like, what did I read? You don't want to do that.
Yeah.
And we're training your brain to be able to think and process information as you read it. And so you want to read actively. So like if you scroll up really quick, when we read this, right? We were like, okay, sorry, so okay, oligosaccharides, these are sugars, and then
Hmm.
mag 3 is like, the X here is 3, so there's 3 of them. And then we talked about hydrogen bonds with these. And, you should be thinking, okay, the alanine's a little weird here, right? And then we say NAG3, NAG monomer has issues. So we have to do this titration. So when we see titration, we want to be thinking equivalence point because 99% of
Hmm.
the time, if they talk about titration, they're going to ask about the equivalence point. And
Yeah.
anticipate what they expect you to answer it as, because people might think the equivalence point is same volume, same concentration, but it's the moles part. And
Hmm.
also the insight that we had about the equivalence point being equal to the moles of the analyte. That helps you answer that question because what people see in the question stem is NAG3. So they
Hmm.
get this for NAG3, and that's why you had the choices with the 25 in it, right? Uh,
Makes sense.
so like the question stem literally says NAG3, but that doesn't mean that's what we use, right?
Hmm.
But anyway, and then when we looked at this thing, and then, I asked you about what does it look like, does it look a little familiar? That can also greatly help. So you want to just get to the point where, and you'll get to the point and you're getting there. You're like, getting better every single time I meet you. So you're getting to the point where you are able to read a passage actively, understand it, um, and you'll get to the point where you can then anticipate what they'll ask. And that's pretty much where you're gonna
Okay.
get to. Yep.
Yeah, I think the biggest problem has always been like balancing out, trying to find a way to
Mhm.
yeah, actively read,
Yeah.
but also get used to the clock. But I think I
Yeah. So
just
now with
threw
the
myself into the clock rather than
yeah.
probably
So now
building
with
something.
the
But
checkpoints, now with the timing checkpoints, it means that you're scheduling times when you check the clock. So you don't have to check it aside from those checkpoints. Like if we didn't do the checkpoints, it's like you would have to look at the clock often, right? And that's gonna
yeah.
take time itself, but also mess with your concentration. But this way you can concentrate purely on the stuff that you're supposed to concentrate on, and yep, you'll have your checkpoints. Yeah.
Okay. Guess we can go to the next one. Oh, good there. In ITC, what's ITC?
It's
Okay,
just
it's
that's
isothermal titration calorimeter. Experiment is conducted by injecting compound one, okay, we don't really know what compound one is, into a solution of protein A, giving large measured heats and a high affinity constant K1. A CITC experiment under identical conditions, but in the presence of 10 millimolar compound 2, okay, gives the same heat curve and K app equals K1. What changes to the experimental conditions can result in the measurable heat differences and K app is less than 1, K1. Okay, I'm confused because I guess two compounds. Seeing there's apparently one of them, when we throw it into protein A, the solution protein A has a high measured heat, high affinity. Then the same CITC, which is different, we throw in compound 2, but apparently it has the same K app and K1. I'm not sure.
okay. So in the passage, the K app, what was that?
Uh, I think it was Apparently it's the, yeah. So they're here related to the affinity constant of nag to knag.
Okay. So, but why didn't we just measure KNAG? Why did we have to do KApp?
Because it seems like depending on the amount of sugars that nag has, it has a different binding affinity.
Or so NAG itself is just one sugar, right?
Yeah, one sugar, yes.
Okay. And they said that we couldn't measure KNAG directly, right?
Yeah.
So that's why they used CITC, right?
Hmm.
So, and that gave you a KApp, which can then help you figure out KNAG, right?
Yeah.
So, so okay, initially, right, we had NAG3 as the actual um substrate, right? Right? And we were able to directly measure KNAG3, right?
Hmm.
And then we had a new substrate, which was what?
The compound, what in this in the question, the compound two, the new substrate?
Oh no, just in the passage.
The nag, sorry, the nag.
And our K was the K app, right?
Hmm.
Which can roughly be a stand-in for KNAG, right?
Makes sense.
All right. So now in the question stem, when they use compound one into a solution of, oh, I should have said, so the protein here was the Hue lysozyme, right?
Yeah.
Okay. So here, compound one into some solution of protein A gave you K1, right?
Yep.
And that's could be analogous
The
to
K
something.
nag three.
Yep. Would it be analogous to that or the KNAG?
Well, it says it's a high affinity constant, so I do think that it could be analogous to K nag three, right?
Exactly, right? Because the NAG3 has a high affinity, which is why we can directly measure KNAG3.
Yeah.
NAG itself has a weak affinity, which means that we can't measure KNAG directly.
Okay.
So we could say, so K1 can be analogous to
K
KNAG.
nag. Okay.
Compound 1 can be analogous to what?
Essentially nag three.
Good.
And
Compound, yep.
compound two, I guess, would be nag.
Hmm. Yep. And then the K app could be the K2 or K for the compound 2, right?
Hmm, okay.
Good.
Makes more sense.
So, yep. So, okay. Now, when the concentration of compound 2 is 10 millimoles, K app is equal to K1, right?
Hmm.
So this, oh yeah, so let's actually turn this into like the analogous stuff, right? So K1, so the KNAG3 is K1 over K.
K2.
Yep,
Okay, okay. Or K2, sure.
yep, and that's equal to I don't know what the y-intercept would be, but you would get K, the KNAG here is going to be the K2,
K1, K2. Okay. Oh,
um,
right, K2. That makes sense. K2. Right, you're right. You're right. K2.
times the concentration of compound 2, right?
Yeah,
And I don't know what the y-intercept is, so
sure.
just leaving it like this. So, okay, when k app is equal to k1, meaning this is 1, that happens when the amount of compound 2 is 10 millimolar, right?
Mm, okay.
Okay, so
That makes
now
sense.
they're asking what change to the experimental conditions can cause, instead of them being equal, can cause the K app to be less than the K1.
Okay. If that's the case, then we know K1, okay, so we want to essentially decrease Ki.
Correct?
So we would have to find a way to decrease the amount of K2, I'm guessing, right?
So
Like,
just you could just kind of leave it there because here K app was K nag, but we still kind of dealt with it as K app.
all right, and K-up was the whole thing where they would try to do the titrations to try to figure out
Yep, yep,
how
yep.
to, right, okay.
So okay, so like we know that when we have 10 millimolar of compound 2, K1 over K app is 1, right? Because they're equal.
Mm-hmm.
Now, if K app decreases,
All right.
what
So
happens with the overall number?
it would increase.
It would increase, right?
Yeah.
And so for that to happen, something here must increase, right?
Yep. Let's go up.
So what do you think would increase here?
Some sort of either it would be the this two, compound two, or I guess the K2 somehow.
Yep. And the K2 is really just, kind of like K app here. Um, but yeah, if this left part increases, the compound 2 concentration should increase, right?
Yeah.
Mm-hmm.
Okay. So I guess it would be, I mean, in this case, we would just have to increase the concentration of compound two in the second titration.
Yep.
Oh, okay.
Mm-hmm.
Mm. Yeah, I think that's the last one.
Mm-hmm.
Okay.
Yeah.
All right. I think I got more questions on this CP thing.
What was that?
I think I have more questions on the CP stuff, if that's okay.
Yeah, yeah.
Okay. Oh, no, not this one. No. Just wanted to do this. I wanted to do this question seemed really complicated. I kind of just guessed, but I was like, I don't know what to decide. And the last time, because I also did this section back in August as well. But yeah, I think I got it wrong that time too.
Yeah, so this is a notorious circuit problem. Um, that's likely going to be tougher than what you would actually see, but um, so Kirchhoff's rules. What do you?
Yeah, so there's the junction rule saying that like let's say, okay, I'll point it out. Like let's say if you have 6 amps of current coming through here, it would split into 4 or 2, it would split in some direction.
Okay.
And then he also had the voltage drop. So the essentially the voltage drop throughout the circuit will equal to the overall voltage, so it should be 0.
Yeah,
Um,
so the
yeah.
voltage drop across any loop
Any loop.
is 0. So
Yeah.
that's that's one of the more complicated ones, which unfortunately we have to use here. So
Mm.
first of all, um, what you said the junction rule also.
Yeah, so if let's say like the current, or let's say the current's going through this, current's going applying here, and then it just splits into whatever current it needs to or wants to, I guess.
Is this a junction?
Yes, this is a wait. Yeah, I'm guessing so. I'm gonna say yes. I'm gonna say yes. I think it is a junction, right?
So what what's like what's this?
Oh, it's a voltmeter. So those are the points where it's, I mean, I don't know though. I mean, I know it's a voltmeter. I know it measures the potential difference,
Mhm.
but I don't know if the points are for potential difference or the points are for, actually, wait, makes sense. Yeah, I don't think the current would go through because the the voltmeter is put in a way where it's not supposed to affect the current in the circuit.
Yeah. So let's have so what's this A thing that I made?
That's the ohmmeter, not ohmmeter. It's a
Mhm.
voltmeter, and
It starts with an A.
ammeter.
Yep. Which
Okay.
what does that measure?
Current.
So if you want to measure, for instance, a current that goes through this resistor that I drew,
Hmm.
you would need the current, you would need to set the ammeter um, in series with the resistor because, well, if two things are in series, the same current goes through them, right?
Yes.
Okay. So so the ammeter is meant to measure the current that goes through, I'll say whatever, resistor or R here. So that means that your ammeter is going to be in series with the resistor, and its resistance would be 0 because, well, if it was larger than 0, you're going to lose some of that current, right? So we want
Yes.
the ammeter to be in series to the resistor and have a resistance of 0. Okay. Now, a voltmeter, let's say for this, if you wanted to figure the voltage across this resistor, is going to be in parallel to the resistor, but if you have the current split here, you're not going to get an accurate reading of the voltage drop across the resistor. So that means that the voltmeter has a resistance of infinity because you don't want the current to go into it. Okay. So is this a junction?
No.
Correct. Good.
Makes sense now. Okay.
Yep. So, okay. So we see that. Let me use, okay, blue. So this is, I'll call it I naught. And this is a junction, right?
Hmm.
Okay. So the current that goes into R1, I will call I1. And the current that goes into R, I'm just going to write as I, right?
Okay.
Now, and then this one here exits R1, and it doesn't get split here because that's not a junction because the voltmeter has an infinite resistance.
Yeah.
So the current that goes into resistor 2, I can call I2.
We wouldn't call it I1. Aren't they technically in series? No?
Yep, yep, yep. So I'll call it I2, but yes, I1 is equal to I2.
Okay.
And then here, the one that goes into R3, I'm going to call I3, but you're probably going to say something about that.
It's the same thing as I, right?
Yeah, good. So now the voltage drop across a loop is going to be 0, which is kind of an awkward way of writing it because it's going to be like voltage
Oh boy.
minus like voltage 1 is equal to 0, let's say, and then voltage 2 minus voltage 3 is equal to 0. And I mean, but it's simpler to just do like, then add V2 on both sides. Um, so V is equal to, or sorry, V1 on both sides. And then for this one, you can just add V3 on both sides to get V2 is equal to V3, right?
Mm, okay, I see what you're saying.
Because
Okay.
yeah, the loop rule is like, voltage drop across the loop here is 0. But like that, that means we're writing it like this, but that doesn't help us that much. So I'm gonna just add the V1 on both sides to get V is equal to V1. That way I get an actual equation, right?
So you wouldn't do like V minus V1 minus V2 minus V3, like that wouldn't make sense,
Correct.
right?
Yeah. Because
Okay.
these are two loops, right?
Oh, right, because the current can go through this way, or the current could go
Yeah.
through that way.
So
Okay.
in pink, that's one loop. In orange, the other loop.
Right.
Okay.
Makes sense.
Yep, yep. So okay, now for this, I can just plug in the like Ohm's law, right? So I just regular I R regular, meaning this one, right, is equal to I1 R1, and then here I2 R2 is equal to I3 R3, right?
Okay.
And there's a lot of things you can do from this point, but I mean, I'm remembering like you remember like system of equations.
It's been a while, but
So it's like, it's like whatever, like 10 is equal to 2x plus 3, and then 7 is equal to 1x plus 2. I can kind of,
right, you just do 3x and then 5 or something.
yeah, I can like subtract them. I can, well, for this, because it's like with these parts, I can't divide them. But if it was like 10 is equal to 2x and 7 is equal to 1x, I could divide these, right?
Right.
And I would want to get rid of the x's, right? To get rid of the long
Mm,
terms. So here I can do that. So I could do here, I'm gonna write it on the left here. So I R is equal to I1 R1. Oh, and then I1 is equal to I2. So I can kind of like divide it by the I. I'll just do this first and then I'll do the equals. So I2 over R2. And then this one would be divided by I3 times R3, right?
okay.
Like I'm just taking this and I'm dividing it by this.
Okay. I see what you're doing.
Yeah. Okay, and now since I1 is equal to, oh wait a sec. I1, oh, hold on.
Also, just to make sure, I guess we're going back to this, like
Yeah.
this V, this voltage, this V that we have here would denote, we're denoting this, right? So essentially it's subtracting
Yeah,
this one minus this one.
yeah. So I made, so I'm gonna make it so it's actually like that. Now it's more consistent, right?
Okay.
So okay, so you'll see what I mean. So
But because you wouldn't do like V this voltage minus this voltage. You
okay,
would have to do
yeah.
this voltage and this voltage.
Yeah, because the orange loop involves R1 and R2, and the
Yeah.
pink loop involves R and R3. So I want them to be aligned, right? So I because I had V2 minus V3 here, and here I had V minus V1, but I messed up that alignment. So I changed it to V1 minus V. So we basically have this part is the top one. This one is the top one, right?
Mm.
Yeah. So okay. Now this means that um okay, equals 0. So in other words, V1 is equal to V, V2 is equal to V3, right? And then I1, R1 is equal to IR. Then here I2, R2 is equal to I3, R3. And I can divide the stuff on like this into this, right?
Yeah.
So I would get I2, R2, like this, is equal to I 3, R3, right?
Okay.
And since I1 is equal to I2, these cancel, right?
Mm-hmm.
And since I is equal to I3, these cancel, right?
Yep.
So now we have R1 over R2 is equal to R over R3. Solve for R, we just multiply R3 on both sides.
Oh shit.
Yeah,
Yeah. Okay.
this is called a Wheatstone bridge. It's a way for you to figure out the resistance of an unknown resistor using a variable resistor.
Okay. I see what you did there. This makes complete sense. But like this, I don't know why. Like for me, it's like, I mean, because this would be if you said this is V1 and then you said V2 here. But like for me, if the circuit is going, if the circuit gets split and it's going this way, wouldn't it just be V1 minus this voltage here?
So,
And this?
um, so there's something in the question stem that I guess I didn't address. Go to the question stem.
Yeah. Yeah, it's a question, right? Yeah, this is a question.
Yeah, of course. What am I talking about? Oh, voltmeter reading is 0. If the voltmeter reading here is 0, it means that this and this have the same uh voltage. So that's why I was able to put this in this.
What meaning is zero? Okay.
Mhm. So yeah, if the voltmeter reading is 0 here, it means that the voltage like between this and this are equal.
Oh, because that means essentially the potential difference between them is zero.
Yeah. And it's equal
Mm,
for
that makes
R2 and
sense.
R3, yeah.
That makes sense.
Yep.
Okay. What do you think the biggest takeaway what I should get out of this is, to be honest? Do you have an idea?
So I'm assuming all the other circuit stuff makes sense to you, or maybe not, uh but the so like so okay, I'm assuming that you know like how to do like resistors in series, how to add them, resistors in parallel, how to add them, that kind of thing.
Yeah, I mean
Throw in some capacitors in there too.
yeah.
So like granted that if you understand all of that stuff, then the takeaway here is Kirchhoff's loop rule. And um I'll have like a good follow-up to this that um let me get that for you. I'll have it for you like that you can do like perhaps for like homework or something. Let me get it.
Sure. In the meantime, I'll try to go to the next question.
Oh yeah. We're gonna have to wrap up. We could probably do like one more.
One more? Okay. Ooh, let me see.
Mhm. This direct
Do you by chance? I tried to check, but I don't know if you do. Oh, oops, my bad. No, it's searching. I'll check in a second. Do you by chance have any like openings on Friday?
You're saying this Friday?
Yeah. Is there any
Oh
chance?
no. I'm gonna be out for the Thanksgiving weekend.
Oh, okay. Okay.
Yep, yep. So that's tomorrow, Friday, Saturday, and Sunday. I'll be back December 2nd.
We'll be back December 2nd. Okay. I want to make sure that I didn't randomly put you on. Oh, okay, okay. Okay. Yeah, I didn't put you.
Yeah, it seems like we have a session on Tuesday the 3rd.
Yeah,
Oh,
yeah.
and then another one on Wednesday the 4th. So we have a 2 hour one on Tuesday the 3rd and a 1 hour one on Wednesday the 4th, is what I
Yeah,
see.
I put those because right when I take my full ends, I want to just make a long review with you to see if what we can do.
Yep. Yep, yep.
Um,
Oh, and then yeah, so it would be good to do your blind review before, like you'll probably do it like on Sunday or something. Um,
yeah.
so like so yeah, when we meet on Tuesday, it'll be after the blind review.
Okay. Trying to quickly go over which one of these questions I would like to go through. It's on the BB section. Uh,
We do like probably like a discrete, another discrete or whatever.
okay.
Yeah. And the I emailed you the other
Okay.
circuit question.
I think we can stop after this question, honestly.
Yep.
I know it's not discrete, but in this passage, they're kind of just talking about like diameter and like arterial diameter and like blood pressure and resistance. And I don't
So
know what
so I'll quickly show you like um the proportionality thing that I was talking about. So here
oh, okay.
they're talking about um G actin getting converted into F actin, right? Through
Mm,
actin polymerization. But depolymerization going backwards will be through lat B.
yeah.
This is kind of like a schematic. Now, so like yeah, in BB, the stuff that I'm gonna show you like partially right now is gonna be more useful for BB. So that's the schematic thing, and now the proportionality, meaning if you have uh so okay, like lat B is gonna be proportional to G actin over F actin, meaning lat B increases the amount of G actin and decreases the amount of F actin. Okay.
Okay.
Now let's look at table one. So table one shows us various things, right? From left to right, we have arterial diameter decrease. We have phosphorylated LC20 like increase and then stay the same. Phosphorylated calponin increase, stay the same.
Hmm.
G actin decreases, right?
Yeah.
Decreases as the arterial diameter decreases, right?
Mm.
So, and if the arterial diameter decreases, that's vasoconstriction, right?
Yes.
So vasoconstriction would be proportional or inversely proportional to G actin, which means proportional to F actin, right? So an inverse proportion means that, so like I could also say just 1 over G actin, meaning the more vasoconstriction, the less G actin. and we see that here. And if you have, and we know that G-actin polymerizes into F-actin. So if we have less G-actin, we must have more F-actin.
Yeah, because it's getting polymerized.
Yeah. So proportionalities like this are going to be like a godsend when you do the BB passages that are just full of 1,000 acronyms and inhibiting like inhibitors, and there's so many like things to that are difficult to keep track of normally. So you'll see that when we do use proportionalities, it can be turned into like a logic truth table kind of thing. Like, you know, uh so like this, so if they told us that G-actin turns into F-actin, we know that, that you can't have an increase in one without a decrease in the other. So so
Yeah.
yeah. So yeah,
Okay.
I'll show you more like, probably yeah, the next time we meet or something. Like, but yeah, the proportionality stuff and the schematic stuff is going to be really useful.
Okay. Yeah. So the only thing I had, like the last question is like, I don't understand this. It says in this like solution, it says arterial diameter decreases with increased pressure. That corresponds to a decrease in resistance, meaning flow stays relatively consistent. I thought like if you decrease the diameter, wouldn't there be more resistance?
So this is relating it to like what is it? The like continuity equation or something. But we don't worry too much about that because it's really just like the pressure change in pressure is like the blood flow times the resistance. I think it's like, so what they're doing here is they're showing you like they're essentially taking Ohm's law and making it analogous to like blood flow. Meaning,
Okay.
so if it's something like this current is analogous to the flow, and this is analogous to the change in pressure. So, but yeah, we can go into that yeah, like next time. But
Okay. Okay.
yeah,
I'm
we
gonna
don't
take a look at
even
that.
really need this. Maybe to eliminate some of the other choices because I haven't seen them, but does it make sense why it would be A based on this table and the proportionality?
Okay. Yeah, I understood the path. Like I did pretty good on this pass. Like I understood it, but it was just a weird bit that sometimes
Yeah.
is confusing. But I'll try to look into that delta P Q equals thing. Okay. All right, cool. How much would it be for today?
Um, one sec.
Also, is there any way that you can also like possibly upload the BB content diagnostic that we did?
Um, one sec.
I know you say you got backed up a little, but it's fine if you can't.
Here, I put this in the chat. So you have your flow equation, which is, flow is equal to our area times velocity. And then we can apply essentially Ohm's law to it to get your flow rate is equal to your change in pressure over resistance. So, and then that could also be related to the Poiseuille's law. So, yeah, you can take a look at that. Yeah, in terms of the videos, I have, let's see.
Um,
Yeah. So yeah, for the videos, Yeah, I have that like a backlog, but I'll try to get them by like next week definitely. But what we can do like moving forward is I can let you record the session also.
Okay,
That way
perfect.
you'll have it.
Perfect. Okay,
Awesome.
awesome. All right. So how much was it?
Oh, let's see.
150. Okay.
Yep, yep.
150 is good? All
Yeah.
right. Well, man, enjoy Thanksgiving.
You
I
too,
will
all
see
right?
you.
Good luck on that practice test, and yep, I will see you like